Alright, welcome back again to the channel, and now we're starting with the third video, if I'm not mistaken, for the radioactivity and nuclear physics thing. So first video was all of nuclear physics, and then we looked at something related to radioactivity. Now we're going on to the third video, which is going to cover other concepts in more detail. So something else which is important is basically the detection of radioactivity. And in your syllabus, you basically have these three instruments that we look at for detecting radioactivity. Now, a lot of people do know about the GM tube and the counter, but a lot of people do not know about the cloud chamber, the cases where it's used, how does it work, and the cherry on top was that it was asked in the last year's exam series. So that's what we're going to look at today. A lot of people asked me to do this, so here this is. So the first thing is called a cloud chamber. So this consists of air and alcohol vapor in a chamber with a transparent window for viewing. And as radiations pass, alcohol vapors condense on the path of the radiation in small droplets, and this produces tracks which can then be basically captured or frozen in place by cooling this with dry ice. So that basically keeps the tracks which we can then view. So that's what is also shown on this diagram. So there is air in this box. You have a felt ring soaked in alcohol. This is a transparent lid from which the observer can see what's happening inside. This is light for the purposes of illumination, and this is a radioactive source which is placed inside this box. So what's going to happen is that as decay happens, as this emits radiations, this would go out in different directions of this box. So the alcohol or the alcohol vapor would condense on the tracks, and we freeze that in place by this dry ice configuration. Now this also basically works of the idea of the ionizing ability, because the radiations passing are basically going to cause ionization in the air molecules, and the alcohol vapors will basically condense on that. So now the idea is this, that these only work for the much more ionizing radiations, which is basically alpha. So this works primarily with alpha, and this can also work with beta and gamma to some extent, but primarily, as your syllabus says, we do use this for the detection of alpha. And also the amount of tracks we see is basically the rate at which decay is happening. So the number of tracks seen indicate how fast decay is happening, or you can say by that same token how much radiation is emitted. All right, so this is how the tracks for each of these look like. For alpha, it's straight tracks like these. This is primarily what the cloud chamber is used for. For beta, it's long curvy lines like this. So let me write this. So this is straight tracks. These are long curvy lines, and these are short and broken tracks. So that's how it looks like for each of these. All right, so that's the idea here. The other piece of equipment that you need to know how to use and how it works and what it's made up of is the spark counter. So for the spark counter, we have a metal gauze. So basically like what those window coverings are made up of. So that's fine wire gauze that we have here. We have just a wire on the other line, and they're connected to a really high voltage supply. So this is like a plus 1000 volts appearing here, and this is basically ground according to this. And we are intentionally not making this a complete circuit, because if we make this as a complete circuit, current would start flowing, and it kind of defeats the purpose of what we're trying to do here. Somewhere above the gauze is placed the radioactive source. What this is going to do is that as radiations go out into the air, they're going to again ionize the air molecules it's going to create ions, and across this really high potential difference, these ions would jump. So they would jump from the gauze to the wire, because this is a really high potential difference, right? So the charge is going to make these jumps. And it's the same idea, for example, when you are, for example, in winters, when you're walking with slippers in your house, and when you touch a door handle, why you see a spark is because of that charge being, it suddenly jumps across two surfaces. So the same thing is going to happen here, that these ions are going to jump across this huge potential difference, and that's going to lead to sparks. And by counting these sparks, we can again have an idea of how much decay is happening. So this is also written here. So high potential difference between a wire and gauze separated through a small distance for us to see those sparks. As radiations ionize the air, sparks are seen between the gauze and wire. And the number of sparks basically indicate the rate at which a nucleus is decaying. As I said repeatedly, both apparatus work well with alpha only, since it is the most ionizing. For beta and gamma, we use the third apparatus, which is known as the G.M tube. So the Geiger-Muller tube, it basically looks something like this. So you have your radioactive source, which is again going to go out and enter this tube. In this tube, we have an inert argon gas. So basically from chemistry, you know this is in group 8. This gets ionized by the radiation, and we provide these different voltages so that, for example, the negative ions go towards the positive electrode, the positive ions go towards the negative electrode, and this flow of ions basically create a current, which we can then amplify and feed to the rate meter, which shows us some readings. So this basically also gives us an idea of how much radiation is basically being detected. So it tells us how fast something is decaying. So the flow of current creates a voltage pulse, which is amplified and sent to the rate meter. It may also sometimes be connected to a loudspeaker, which keeps giving you those ticks or the number of clicks, which are then counted by the counter. So count rate is measured in units of counts per second, or in the units of counts per minute. And because we know radioactive decay overall is a random process, this applies to all three of the apparatus that we have seen here. Because of randomness, in this case only, so what we're talking about for this case would also apply to the other ones. The count rate can fluctuate, right? So sometimes it could be more, sometimes it could be less as well. So that's the idea of this thing here. Background radiation. So this is radiation which is always present in the surroundings, even with no source placed. And this can be measured by checking the count rate on a GM tube without any source placed. The radiation which is then measured in an experiment is sometimes corrected by subtracting the background radiation, because the radiation that you would have normally would include both the radiations of the source and of the background. So by doing this, you can measure the background radiation, and then you can correct it by subtracting the background radiation. So common sources of background radiation, you have something called radon gas in air, which also contributes to background radiation. You also have cosmic rays from the sun, which also are an important source of background radiation. Apart from this, food and drink often do also have sources of radiation. For example, like the potassium in bananas, they also contribute to the background radiation. And lastly, rocks and minerals often also have elements which are naturally radioactive, and they also contribute to the background radiation. Now regarding radiation, because of the ionizing effects, radioactivity may cause some of these issues. So for example, like skin cancer is a very common hazard of radioactivity. This can be caused by the ionizing effect. This also leads to burns. Skin cancer and burns are basically the same thing for your paper. Apart from this, it also causes cell death or cell mutation, which also eventually leads to cancer. And apart from this, it causes cataracts in the eye as well, which eventually do lead to blindness. So for safety, what can we do? So we store radioactive sources in what is called a lead lined box. So because lead is something which can block even gamma to a great extent, that's why it would also block the other sources such as beta and alpha. You should also aim to minimize the time of exposure to these radioactive sources, and you should also aim to maximize the distance from the source by using, for example, tongs or forceps for handling. These radioactive sources. So that's the idea of this thing. Now we're moving on to the concept of half-life, and I think this is where a lot of people do get stuck. So for half-lives, you'll only need to ever see this video to understand half-lives for your O-levels or IGCSE. So the idea of half-life is this, that we know that when something is decaying, that's basically giving rise to emissions. And because of those emissions, the number of nuclei that we have is decreasing. How we define half-life is that we say this is the time taken for the number of nuclei or the number of atoms in a sample to halve. But also the idea is this, that when we talk about radioactive decay, we previously said that radioactivity is a random process. So we basically can't use an equation to say that, oh, all right, at this time I'm going to calculate exactly how much of the atoms I have left. We use something which you've probably heard of in O-level math, which is probability. So there is a constant probability of decay. Now let's say, for example, if you have a dice and if you roll a 6, then the probability of you getting a 6 on any throw is 1/6. Let's say I have 12,000 fair dice. Let's say I roll all of them. What is the expected number of 6s I would get? Then that would be 12,000 multiplied by 1/6. So I can get 2,000 6s. I can expect 2,000 6s. All right. Now, let's say I take half of those dice away. So from 12,000, I now have 6,000. And there's still the constant probability of 1/6 of getting a 6. So this time 6,000 multiplied by 1/6, I would expect 1,000 6s. Let's say I halve it again. Now I have 3,000 die. So 3,000 dice multiplied by 1/6, now I would be expecting 500 6s. That's basically the idea that's also in place here. If my number of nuclei or atoms are decreasing, the count rate that you would get on a GM tube, which is also called activity, that's also going to decrease. So initially, as you'll also see in the graph, the number of nuclei initially decreases very fast because you have a lot of nuclei, but then as the nuclei start to decrease, the activity, the rate at which decay happens, also decreases. So that's why you can also give the definition of half-life according to this. So while you can also say it's the time taken for the number of nuclei or the number of atoms to halve, you can also say it's the time taken for the count rate or the activity of a sample to halve. Now this is also shown in this graph. So let's first think about the theoretical graph, which is shown in blue, and then we'll talk about the orange one. So initially you have some number of nuclei n. After one half-life elapses, which I've shown using this, so T subscript half. After one half-life, it becomes half of whatever it was, so it becomes n. From n, it becomes n by 2. After another half-life has elapsed, it becomes half of this, so half of n by 2 is n by 4. After another half-life, you can see that it becomes half of this, which becomes n by 8. So you can see in the first half-life, the number of nuclei decreased by a lot, but in subsequent half-lives, you can see that it decreases by less and less amounts. And the simple reasoning for this, as the number of nuclei decreases, the activity or the rate at which decay happens also decreases. So that's the idea here. And theoretically, the number of nuclei never becomes zero. That's just how the theoretical aspect of this works out. In reality, you see that it's not a very smooth curve like this. Rather, it's something like this, where you have like zigzags and you have these, sometimes it's going up, sometimes it's going down, sort of a trend. So that's because in reality, you know that radioactive decay is random in nature. So for example, if you are expecting after a certain time for the nuclei to be, let's say this much, let's say less decay happens, so you actually have more than what you expected. Again, that's just randomness. Similarly, at this time, you were expecting this number of nuclei to be there, but you have less than that because more decay happened as compared to what you were expecting. That's the same thing as you could also apply with the dice. For example, if I said that if I have 12,000 dice and if my probability of decay is 1/6, I was expecting 2,000 sixes, but you know it could be more, it could be less, because it's all dependent on probability. So the jagged nature of this curve actually shows the random nature of radioactive decay. And now, because we'll be going on to the half-life questions, for half-life, I want you to remember this. Always think in terms of the number of half-lives, because half-life is not a linear process. It's not like this, right? It's a curve. Between any half-life, the number of nuclei halves. So that's what I want you to think about. Now, this is an example that I've come up with after going through a lot of past paper questions. It covers every possible type of half-life question that can be asked in O-levels or in IGCSE. So this question says a radioactive sample contains 2 × 10⁹ nuclei. Its half-life is 4.5 minutes. So after 4.5 minutes, this number of nuclei would halve. Calculate the, in part A, number of nuclei remaining after 9 minutes. All right, again thinking about the number of half-lives. So if 9 minutes is the time, so this is 4.5 minutes. So I know 9 over 4.5 is 2 half-lives. And now I'll be making what I call an arrow diagram. There's no such name for it, but that's what I'll use. So I know that at first it's 2 into 10 to the 9 nuclei. Each arrow represents a half-life. So if I have 2 half-lives, I'll be making this until I get 2 arrows. So after 1 half-life, this would halve. It would become 1 × 10⁹. And then another arrow, after this it halves again. It becomes 0.5 × 10⁹, which I can also write as 5 × 10⁸. And this is the number of nuclei that remain. All right, so that's how you do a very easy type of question. Part B. This one said the number of nuclei remaining. This one says the number of nuclei decayed after 13.5 minutes. Okay, so 13.5 minutes, again, let's first figure out how many half-lives that is. So 13.5 divided by 4.5 gives me 3 half-lives. So I already know what this looks like. So above I made it for 2 half-lives. So that's this. Let me just copy this to save some time. So 2 × 10⁹, 1 × 10⁹, then you'll have 5 × 10⁸. And you need to have another half-life because you have just 2 arrows up till now. In fact, let me take this here. So after another half-life, this is going to halve again. This is going to become 2.5 × 10⁸. This is the number of nuclei which are left. The question is asking for the number of nuclei that have disappeared, that have gone away, that have decayed. So the initial number of nuclei was 2 into 10 to the 9. Subtracting from this the number of nuclei remaining after the set time. So when you calculate this, you would get the number of nuclei that have decayed. So 2 into 10 to the 9 minus 2.5 into 10 to the 8. Let's work this out. So it turns out to be 1.75 into 10 to the 9 number of nuclei that have decayed. Part C, the more tricky type of question, the time by which the number of nuclei becomes 6.25 into 10 to the 7. So here no such, time is given, and instead you have to find the time. So for this, there's a sort of trial and error sort of working where you just have to go through with this diagram until you hit the number that you desire. So for example, I'm going to copy this again for part C. So I need to go till this number here, which is 6.25 into 10 to the 7. So let's go on. 2.5 into 10 to the 8. Let's halve this. So this is going to become 1.25 into 10 to the 8. Let's halve this again until we hit the number. So that's what we'll keep doing. So divided by 2, this does give me 6.25 into 10 to the 7. Now remember that each arrow shows the number of half-lives. This is 1, 2, 3, 4 and 5 half-lives. 5 half-lives, each of which is 4.5 minutes. So if I multiply this out, this is 22.5 minutes as the time elapsed. For part D, I want you to do this without considering the initial number of nuclei, and trust me, it's going to be easier this way. So the time by which the nuclei become 1 over 128 of the initial value. Alright, so let's say that initially I have some number of nuclei, let's call that A. Or in fact, let's call that N. After one half-life, it's going to become N by 2. After another half-life, it's going to become N by 4. After another half-life, it's going to become N by 8 because it's halving. Then N by 16. Then N by 32. Then N by 64. And then N by 128. Computer science students know these numbers on the back of their hands, so this is very easy to them. So now what you can do is you can count the number of arrows. So 1, 2, 3, 4, 5, 6 and 7. You have 7 half-lives, each of which is 4.5 minutes. So multiplying these, this time turns out to be 31.5 minutes, after which the number of nuclei would become 1 over 128 times 1 over 128 of the initial value. So do keep in mind that for this you didn't really need the initial number of nuclei. So if it's not given in a question like this, and these have been asked in the past papers, no need to get worried as long as you hold on to the basics. Another question on graphing. This is also something which absolutely terrifies students. So background count rate is given as 30 counts per minute, and the sample has a half-life of 50 minutes. So after every 50 minutes, the half-life, the number of atoms, the number of nuclei halves. And by that same token, the number of counts would also halve, because this is what's given here. So the detector measures an initial count rate, including background, of 310 counts per minute. Plot suitable points and draw a graph of total count rate. Now, the question that I've extracted this from in the past papers actually had an easier part that was just for the uncorrected count rate. So let's first make the corrected count rate. So let's first make it for the corrected count rate, and then we'll talk about the total count rate. All right. So I can see that if this is 310 And if this is including background, so 30 is also included in that. So my first point is going to be 310 minus 30, which is going to be 280. So looking at this graph, so this is probably 225, 250, 275, this would be 280. So let's place a dot here. This is my initial count rate. This is just from the source, so that's what's meant by the corrected, which means just from the source. So that's 280. After this, I now need to plot more points. The half-life is given. So I know that if it's 280 initially, after a half-life, the count rate would also halve. So from 280, it's going to become half of that, which is 140 after 50 minutes. So this is 125, 150. So 140 is probably somewhere here. This is 140, corresponding to 50 minutes. Then again, after another 50 minutes, this is going to halve again. So that's going to be at 100. So this is 75. So 70 is going to be somewhere here, like this. And then after another 50 minutes, which is at 150, this is going to become half of that as well. So this is 25. So somewhere above that, that's 35. Like this, right? So this one is at 50, this one is at 100, this one is at 150, this is the initial. So I can just join all these with a straight line, like, not with a straight line, my bad, with a curve like this. All right. So this is the graph for the corrected rate, the corrected count rate. But if I talk about the total count rate, which is basically what the counter would be detecting, it would also be detecting the 30. Now, why could I not just halve the 30? Is because the background count rate would be constant. It's not going to halve. Yes, the counts from the source would halve, but this is going to be 30 all the time. So this exact curve that I have here, it's going to be the same curve, but in addition, you will also have the 30 counts from the, what do you call it? So in addition, you'll also have the 30 counts from the background. So this would probably correspond to like 310 here. So it's basically the same curve, but shifted up by 30 units because of the background radiation. And this here is the total count rate variation. All right, so this was a pretty comprehensive example, and now hopefully you know exactly how to tackle any and every type of half-life question. So in the next video, we'll be going over the last few things remaining regarding the nuclear processes involved. See you there.